Good morning and welcome to Compass. Our speaker today is John Lodise. He's a fifth-year senior in MPO. And prior to coming to RSMAS, he got his bachelor's in environmental science with minors in physical oceanography and atmospheric science at the University of Delaware. A fun fact about John is that he can quote any episode of Parks and Rec. Today, John will be talking about measuring surface ocean currents using massive arrays of CARTHE drifters.
Thanks, Joe. So today I'm going to be presenting some work that I've been doing, or the majority of the work that I've done for my PhD here, working for CARTHE, working for RSMAS. It seems like all my presentations start in kind of a sad place. The Deepwater Horizon oil spill, 4.4 million barrels over 84 days. That has spawned this huge array of physical oceanography and a ton of different disciplines under the umbrella of oceanography that have been studying oil spill like processes. So here I pulled a satellite image of the Deepwater Horizon oil spill. And just looking at this image, you can pretty easily tell where the oil is. What you can't easily tell is how it got there and where's it going to go next. So a lot of what I'm going to be trying to answer is what causes these surface signatures of this oil, and what are the processes that govern the movement of this oil on the surface of the ocean. And it turns out there's a lot of processes involved. So first it comes out of a deep well. Some of it settles out at different density layers within the ocean, and a lot of it makes it up to the surface and then gets pushed around by winds, waves, fronts, eddies, different circulation patterns, a lot of stuff going on. So how can we study these processes? Well, you can perform an experiment. So my first year here at RSMAS, the Lagrangian Submesoscale Experiments took place. They used the Walton Smith and another vessel called the Mesoscale 8, where we released over 1,000 biodegradable drifters in the course of about a month. And after about 3 months of floating around, this is the data that we received from these drifters. So these 3 yellow squares here are where we released the drifters to begin with. And we see we have some pretty good coverage over the entire Gulf by the end of our study period. And if you squint your eyes and tilt your head, you can kind of get the feel that you're seeing some of the same circulation patterns that you saw within this satellite picture of the oil spill. But now we have to unbundle all that data and get something useful out of it. So a brief outline of what I'm going to be talking about today. Chapter 1 is going to discuss deconstructing drifter velocities to estimate wind-driven currents. Chapter 2, we're going to investigate the production of submesoscale currents along mesoscale features. And Chapter 3, I'm going to touch on some future work. So Chapter 1, wind-driven currents. We're going to focus on this little square of this diagram here. So why study wind-driven currents? We have a pretty limited observational data set of ocean currents right at the very surface. Things like ADCPs, HF radars, and most drifters can't resolve the top few centimeters of surface currents. And models usually treat the upper 1 meter or larger as a single layer, which neglects a lot of wind and wave-induced vertical shear right at the surface. But this shear has a large effect on things that float on the surface that we want to predict the transport of, like oils and plastics. So we need new measurements, bottom line. Luckily during LASER, luckily for me at least, we had some engineering issues, and a lot of the drogued drifters lost their drogues and became undrogued drifters. And through the hard work done by Angelicaza and all, we were able to figure out exactly when the drifters lost their drogue to be able to use these 2 different data sets. And in addition to that, Guillaume Novelli et al. Studied both these drifter types in the lab before actually bringing them to sea, so we have a pretty good idea of how the wind and waves affect the drifter types out in the ocean. Because drifters don't track the ocean perfectly, even though we come pretty close, but there's some measurement errors that you have to be aware of. So again, unique opportunity to study the vertical shear right at the very surface of the ocean. So we're going to be comparing 60 meters draft depth that the drogue drifters are sampling compared to only 5 centimeters that the undrogued drifters are sampling. So our objective here is going to be to deconstruct the full velocity of the drifters into wind-driven velocities only. While we're doing this, we're going to focus on 3 high wind events during laser, and we're going to again observe vertical shear. So our method of deconstruction is as followed. We have the total velocity captured by the drifter, the total drifter velocity, the Stokes drift, which is going to be calculated from the UNCM model, a coupled model, atmospheric, ocean, and wave. We're going to have a regional circulation component, which we're actually going to capture with the drifters before an increase in the winds. And we're going to solve for a wind-driven current. And I also want to mention now that all the wind components that we use are from the UNCM output as well. Last thing, all components are defined for drogued and undrogued drifters separately. So here I'm showing our 3 wind events, the wind records. All the blue dots are the wind velocities taken from the model at the location of the drifters within these corresponding domains to each wind event. And the lines plotted on top of these are just the wind records taken from these buoys when we had available data. And we see that the observations and model work pretty well together. So we're just going to use the model data where we have it next to all the drifter locations. Just to fit the drifter data a little bit better than just using these point measurements. So here's an example of how this velocity deconstruction is going to work. We want to solve for our wind-driven current during our high wind analysis period. We have the total surface current, which is just the velocity of our drifters during this period. So check. We're going to have to solve for or calculate a regional circulation before we see an increase in winds, because those winds are going to disrupt the regional circulation signature. So we need to get that before the winds increase. And then we're going to take the Stokes drift from the model as well and subtract it during our high wind analysis period. So what we're saying here is basically that we can observe the regional circulation here, and the timescales of this regional circulation are going to be long enough that they're not going to change much between here and our analysis window. And I'll show you how that works out. So first we're going to look at some Stokes drift validation. Here I'm showing the 2D wave spectrum from the model and from wave buoy 42040, and the 1D spectrum as well. And here I'm showing the Stokes drift calculated from each of these wave spectrums in time throughout our January high wind event. So we can see there's a slight offset in the peaks between these wave spectrums. But at the end of the day, the Stokes drift that we calculated from both the observed wave data and the modeled wave data agree to a reasonable extent. So we have our Stokes drift. Next, we have to calculate this pre-wind regional circulation. And we're going to do that using our drifters in the area the time before an increase in the winds, and something called a Lagrangian variational analysis to arrive at these Eulerian velocity fields. So how does this work? Well, step 1 is to simulate a drifter trajectory in the Eulerian flow that you want to solve for. And you do so using this equation, where R is the simulated positions, and U is a velocity correction or guess that you start with. Step 2 is to calculate a cost function. So I know this looks complicated, but I'm going to boil it down as simple as I can. So it's a function of the distance between simulated and observed drifter positions. So you simulate a drifter goes this way, the observed goes this way, you want to try and minimize that distance. This H nonlinear is just an operator that is used to calculate a bunch of different drifter trajectories at the same time. And it's just a function of your velocity correction. So you're looking at a bunch of different trajectories under different velocity corrections. You have to figure out which one's the best. How do we do that? By minimizing this cost function. And like I said, we do that by minimizing the distance between observed and simulated trajectories. So we take the gradient of J, and then we use what's called the steepest descent approach along the gradient of J to reach the minimum. B spreads the velocity correction around the drifter's neighborhood of influence, which is defined by a parameter length scale R, which is shown here, this being your drifter trajectory. And then lava then radiates decreasing velocities away from the center. So it looks like that if you hit one drifter. But we have quite a few. So these are each high wind event here, 1, 2, and 3, and then we have drogued drifter, undrogued drifter locations on this side, and the corresponding velocity fields that we make over 1 hour of drifter positions using lava. So now that we have these Eulerian velocity fields, we have to investigate the timescales of them a little bit. So here I've plotted the drogued drifter velocity fields on both columns here. One has sea surface temperature during the high wind event plotted under it, and one has sea surface temperature after the high wind event plotted on it. And we can see that we have pretty good velocity field and sea surface temperature agreement throughout most of it, and not too many changes as you go into a full day ahead, or a full day after our high wind event. So this is just to show with reasonable doubt that our velocity fields are capturing dynamics and they'll last throughout our high wind analysis period. Last thing I want to point out is the length scales of these flow features seem to be on the order of a few tens of kilometers, which fall somewhere between submesoscale and mesoscale dynamics. So we're expecting these structures to last longer than a day, but probably less than a week or so, which seems like it should be good enough for our purposes. So check, we have a pre-wind regional circulation. Now it's time to do this velocity deconstruction. So the drifters travel, we capture them before the high wind event, and then they blow back through the domain, being predominantly wind driven during the high wind event. And some of the data overlaps, which I'm showing here in these black trajectories, and some of it doesn't, which I'm showing here in red. So for the rest of the talk, I'm only going to talk about the velocity deconstruction, where we have overlapping data between drifter trajectories during the high wind events and observations of the pre-wind regional circulation. So these diagrams show the velocity deflection angle from the wind. Here, before we do anything to it, just the full velocity of the drifters, drogued and undrogued. And here, after we remove the regional circulation estimate. Just to orientate you, 0 is in line with the wind. This line is 45 degrees to the right of the wind, and then this last dotted line is 90 degrees to the right of the wind. So we can see that after the subtraction of the regional circulation, which leaves us just the wind and wave component, we fall within 0 and 90 degrees to the right of the wind, which if you know anything about surface wind transport, you know it should be somewhere in that area. So we're pretty confident that we're capturing that signal, especially when you look at the full velocity deflection angles here. You see it less of a collapse in the cloud of the undrogued drifters, but the standard deviation of the deflection angle is collapsing as you go along from 10 to 20 meters per second in wave magnitude. So the timescales of the regional circulation seem long enough for our method of subtraction. So we're going to say our hypothesis checks out. So now we can look at velocity deviations from the wind. Here, this is the wind and wave driven component. So the same plots that I'm showing here, just binned and averaged with 1 or plus or minus 1 standard deviation as error bars. Stoke drift, we can see, is pretty much in line with the wind, or a little bit to the left, which agrees with theory. We see a deflection angle. Last thing, the middle plot minus the top plot gives us the bottom plot. So wind and wave minus Stoke drift, which is the wave component, equals purely wind-driven component. So we can see there's a 10 to 30 degree deflection between the wind-driven layers, which gives us some indication that there's could be some Ekman-type spiraling dynamics happening there right at the surface of this wind-driven current. The other thing we see is an increase in deflection angle as we go from lower wind speeds to higher wind speeds, which could be an effect of vertical mixing of momentum done by breaking waves and turbulence. I like to think of this as you're stirring up the top few vectors of your theoretical Lagrangian spiral, so you get more of a turn to the right. Now look at the velocity magnitudes are the same. Stokes drift 0.5 to 1.5% of the wind, in good agreement with the literature. The combined wind and wave driven velocity is 1.6 times greater than in the 0 to 5 centimeter layer on average, which lines up well with other studies done in the field, Labs.Agol, and in the laboratory, Novelli. And our wind driven current, we see, shows a lot of vertical shear with the top 5 centimeters traveling 3.4 to 6% of the wind over various wind bins, and the 0 to 60 centimeter layer traveling 2.3 to 4.1% of the wind. Just to show you we're not crazy, this is a comparison to past studies. And you can see that first off, past studies have studied a little bit of deeper layers, 0 to 1 meter, 0 to 2.5, which I think is the shallowest layer next to ours on this chart. You can see that our deflection angles are within the realm of possibilities, and our 0 to 5 centimeter layer is the highest on this chart. Which one makes sense because we're capturing the thinnest layer, so there should be the most vertical shear being represented there and should be accelerated the fastest. There's a little bit of a conversation around the windage being felt by these undrogued drifters, which is still being debated, and we can talk more about that after the talk if anyone would like to. So here, I'm looking at the relative strength of the different forcings, mainly the regional circulation over the total velocity of the drifters during the high wind event. And we can see that the regional circulation is only 20 to 30% of the total current measured by the drifters during our high wind analysis window, leaving the wind and waves to make up the other 70-80%. So you can see this is really dominated by the wind and waves during these high wind periods. To summarize, considerable shear exists between the 0 to 5 and 0 to 60 centimeter layers with a rotation that kind of resembles Ekman spiral-like dynamics. And we see a strong shear between the two layers, with the 0 to 5 centimeter layer being 1.6 times larger. We see increased deflection angles as the wind speed increases, which we think is due to vertical mixing of momentum. And currents are largely controlled by wind and waves during these high wind periods, which shows the importance of incorporating this vertical shear into any type of model that wants to predict the transport of pollutants. So moving on to chapter 2, we're going to investigate the production of submesoscale features along mesoscale features. And for some little motivation, here's another picture of the Deepwater Horizon oil spill, all the oil being captured along this front. I'm not going to try and estimate how big it is. But here's what we can see happening. On submesoscale fronts and eddies, 2D particles that travel on the surface of the ocean like drifters will naturally get caught in what's known as subduction zones or convergence zones and line up along the length of the front. These subduction zones play major roles in the vertical exchange of surface and interior waters and have effect on the transports of dissolved nutrients and gases, biological production, and carbon storage, but have been very difficult to model correctly so far. And once again, we need more observations to describe the dynamics. Quick review of what's mesoscale and what's submesoscale. Mesoscale is anything larger than 100 kilometers and lasts longer than a week, approximately non-divergent 2D flow, which means there's very small, if any, vertical velocity. Submesoscale is only under 100 meters to 10 kilometers and lasts between hours and days. They're strongly divergent and have large vertical velocities, which make them very interesting to study. So our objectives here are going to be to identify energetic submesoscale features along the mesoscale front, observed with drifters and a towed CTD. We're going to calculate kinematic qualities to describe these submesoscale features, mainly divergence / convergence, which will give us an indirect measurement of this vertical velocity. And we're also going to measure the vertical component of the relative vorticity, with large values of which are a signature of strong submesoscale activity. And last, we're going to determine possible mechanisms for the formation of these submesoscale features along mesoscale fronts. So here, we can see a long mesoscale front being formed here in the Gulf of Mexico off the coast of Louisiana. And we also can see some mesoscale structures starting to form along this large-scale submesoscale front. Large-scale mesoscale front. In addition, we have our CARTHE drifters here lining up along this front. I'm going to play this animation here. If you watch right in here and try and look really closely, you can start to see the drifters being captured in some of the submesoscale features that I'm talking about. I'll let that loop one more time. So now we're going to zoom into these drifters going through this box. So you can see them converge along the front. And then these drifters here in the middle are going to get caught in what I'm calling a swirling submesoscale eddy. And you see they start to converge upon each other, which is an indication that there's negative vertical velocities or convergence. And also you can see pretty clearly that there is a lot of relative vorticity being produced there within that eddy. But now to actually put some numbers to it, we're going to have to once again go from drifter trajectories to Eulerian velocity fields to be able to calculate these quantities of relative vorticity and divergence on an actual grain. So to do this, we're going to use an interpolation method called Gaussian process regression, which was first developed by Raphael last year and who has handed down the technique to me. So we assume velocity is a multivariate Gaussian distribution where UD is our known drift velocities and UT is our unknown velocities, or the grid that we want to calculate the velocities at. And all this is saying here is that our velocities here are sampled from a normal distribution or Gaussian distribution that is dependent on a mean function and these covariance matrices. What are these matrices? So each one of these is dependent on the points where we know the drift velocity or the points where we don't know the drift velocity and want to calculate them, or a mixture of both. So what these are doing is just describing how the velocity is going to change about the mean in time and space. And all these k's, we choose to use this covariance function, which is a squared exponential that has terms in time and 2D space, x and y. And this covariance function, that's what I said, describes how velocity changes in time and space. And this is what the whole thing boils down to. It looks complicated because we have these and they're embedded in here. Well, once you have this equation and you've solved for a few terms in here, you can then plug them back into here and then finally get to our gridded solution that we want to reach. And to make it even easier, we're going to start with a zero mean function, with just as making it so that all the velocity reconstruction is totally dependent on these covariances. So let's dig into our squared exponential covariance function. Dependence on time, x and y, meridional and zonal distance. And then we have these, what are called hyperparameters. These RT, RY, RX, sigma I, and sigma N. And these just dictate how the correlations are going to change over time, how they're going to change in the y direction, and how they're going to change in the x direction. And then we have these two sigmas. Sigma I is the standard deviation of all velocities, and sigma n is a bit of a tuning parameter that allows us to account for some observational error in the drifter data. So how do we choose these hyperparameters to get to a Eulerian graded velocity field? So we optimize them using the observational data itself. This optimization procedure maximizes the probability of calculating the observations by tuning the hyperparameters. And this is done by what's called maximizing the log marginal likelihood. Much in the same way that we had a cost function when we were using lava, this is a similar type of function that is only going to be based on observations. This is the covariance matrix between observation points and our observational noise tuning matrix. So just with the input of the observations alone, we're going to be able to, much in the same way, use a gradient-based optimization algorithm just pertaining to all the different hyperparameters and solve for each one. So once we have optimized our hyperparameters, we can then go back and fill in our velocity fields. And finally, something nice to look at. So here I'm showing the divergence calculated along that front. And we can see that they lined up nicely on the front. We have divergence where we think, or convergence where we think we should have convergence. And the velocities look like they're working pretty well. But how do we know? So during laser, there was also a marine radar on the Walton Smith that was taking velocity measurements as well. This was developed by Bjorn Lund et al. And we can try and predict all the velocities here in black using our GPR interpolation method and compare the velocities. So here I'm just showing the GPR interpolated velocities minus the X-band marine radar velocities. And you can see that we're within 0.05 meters per second for the U and the V velocities away from the X-band radar. So that's a pretty good indicator. And then we have the error in terms of the magnitude of the X-band radar. And about 90% of our errors are within 20% of the X-band radar, so we're not doing a bad job. The other thing you can see here is that the U velocities are skewed to the positive a little bit, and the V velocities are skewed to the negative. Now we also know that there's vertical shear due to wind at the surface of the ocean. We also know that the X-band radar, marine radar velocities are sampled at a bit of a deeper layer, around 5 meters, maybe a little bit shallower depending on the wave size. So I decided to look at the wind, which is blowing 8 meters per second towards the south-southeast during the time that these measurements were taken. And that lines up pretty good with the fact that the U velocities are a little more positive and the V velocities are a little more negative. Go back here. Here's a vector showing the wind direction. So a little bit more positive in the U, a little bit more negative in the V, and that's exactly what we see. So we might even be doing a little bit better than these numbers that I'm showing in reality. So now looking at relative vorticity, we see a huge amount of relative vorticity building up almost along this front as the drifters converge. And then if we zoom in on this box of drifters and play it forward, looking at the relative vorticity and the divergence, we see them line up nicely along that front, and then that same eddy that I showed before in the drifter trajectories is going to emerge. And we see a ton of positive relative vorticity and plenty of negative divergence or convergence. And if we take both of those animations and put all the values of relative vorticity and divergence into histograms, we can see that positive relative vorticity is dominating the dynamics here, as well as negative divergence having values of up to 22, 23 over f, which is the Coriolis parameter. We're just normalizing by the planetary vorticity there. So we can see it's dominated by positive relative vorticity and negative divergence, which is really what we're looking for in submesoscale structures. We want to find where surface waters are being subducted into interior waters, or where there's the collection of buoyant particles being captured. So here I'm going to show those drifter trajectories again, and at the same time they traveled over a CTD survey. So you're going to see the transects here advance as the drifters move through these transects of potential density, salinity, and temperature. You also see the drifters enter over here as they're swirling around in the eddy. So we can see over here that there's definitely evidence of some horizontal mixing going on between the more dense, saltier waters on this side and the less dense, fresher waters on this side. And we see this density front penetrates almost through the entire mixed layer. So looking at a snapshot, transect C, which is actually the transect that coincides the best with the time of the drifters being there and the total array crossing. And we can see some evidence of a spiraling eddy here with some horizontal displacement of some slightly less salty water, which I hope you can see. And a lot of subduction happening here, all this fresher water being mixed with saltier water here, and freshwater almost intrusion happening there. So really what we're seeing is one of these spiraling submesoscale features forming, most likely due to the strong relative vorticity seen along the front. So as that forms, it's pushing denser water towards the lighter water side of the front here. And what happens as it twists and turns around, the denser water gets subducted underneath the fresher water. So this pocket right here of high salinity above some lower salinity water and seemingly displaced, I think, or we think, is subducted waters coming from the opposite side of the front. And again, you can see some evidence of some swirling eddy dynamics moving the salinity around from one side of the eddy to the other. And by the last transect here that I'm showing, it seems like the large mixing event is almost done and we have a pretty uniform mixed layer again. So to summarize, we can pretty accurately develop these Eulerian velocity fields using Lagrangian data with the help of the validation and calibration really from the experimenter velocities. There's strong horizontal velocity shear across this mesoscale front, which is most likely the mechanism for the development of these submesoscale instabilities. And these submesoscale instabilities show considerable amounts of relative vorticity and negative divergence or convergence on the order of 10 to 30 F. And we see strong subduction and mixing present within these structures. I'm just going to briefly talk about some future work. We're going to continue to work with this Gaussian process regression technique for interpolating these velocity fields. We're going to study the same type of submesoscale, mesoscale interactions, but with a new data set from the Mediterranean Sea. And we're going to compare these kinematic statistics between the two regions and between different mesoscale, submesoscale structures to try and diagnosis and causality of submesoscale strength. Last thing, I just want to thank a lot of people. The entire CARTHE team that was involved with laser and the acquisition and processing of all this data. Special thanks to Maristella, Milan, and Raphael for helping with parts of this analysis. Huge thank you to my advisor, to and all my committee members, Mo, Annalisa, and Will. And that's all I have. Thanks.
Was that set of observations you showed along the frontal surface, is that basically Mississippi River plume edge?
From the sea surface temperature?
Yeah, you showed
pretty much.
fresh water on one side, salty water on the other.
Yeah.
I mean, is that?
So if you look in here, that's most likely where it's coming from.
Yeah.
But a lot of studies have done stuff in here, looking at right where they meet. So this seems to be a little more stretched out and developed than what other studies have looked at. But yeah, I think it is Mississippi plume water. Fair enough.
So for your Gaussian process regression, how dependent do you think the results are on that assumption that it's Gaussian? And that, like, if you loosened that and used a different sort of analysis, like ELF or something to get your covariance matrices, do you think the results would differ or what?
I really don't know the answer to that.
Well, I have some idea. I mean, the Gaussian processes are applicable to a lot of many Tucker, let's say that, but you don't have to have necessarily linearity or its validity can be really stretched. So I think there's reason to think it's good. It works. But yeah, everybody asks this, Gaussian, but the history of Gaussian, I don't know, maybe more can comment on that. It can be really stretched over many applications which are not necessarily Gaussian. And then there are many natural phenomena that's Gaussian. There's a lot of natural phenomena that follows power laws. So somehow this works in a variety of applications. For instance, if you look at the dispersion, like if you look at the kinematic properties like convergence and vorticity and all that stuff, they are mostly Gaussian with a little of bias. But if you look at other things like how they separate, they are mostly like power laws. So it depends on where you apply it. I think for this application it's okay, but it's a very good question. So you have to be very mindful of what you're doing.
So you're not losing information by fitting next to a Gaussian distribution?
I mean, so you have to compare your errors. I mean, you have a lot of observation errors, okay? You don't know everything. So if you are really, really accurate at some point, you may run into it. But for the oceanic observations, where we are still trying to get like first order idea of what's going on, I think this is okay. But I would like to hear from the front row there. Who developed the method?
It doesn't have to be Gaussian, it can have other shapes, but I don't think it will make much difference in this case, especially because he's using two different scales. So when you get to covariance in the end, it doesn't really look like a Gaussian, it's more steep, goes to the center, and have longer tail.
But it's not a power law, right?
Sorry?
It's not bimodal.
No, it's
power
not.
law.
No.
So if it's a bimodal, for instance, distribution, that's a problem, right? And if it's a power law, it's a problem. So it's like a really good question, actually. I don't know. What do you think?
Well, what I would say is that it's essentially the same method is used routinely for weather prediction and data assimilation. So it's a way you have an observation, how do you spread it out? And the components that go into it are the mean function and the covariance function. And for data assimilation, the mean function is usually taken from whatever the forecast is. And so, it has variability. Here it was taken to be 0, just for convenience. But, another easy, convenient thing is the average of your data.
So we've been toying around with doing different stuff like that, and pertaining to the velocity validation with the X-band radar, This is actually the method that's been working the best. So I've been toying around with trying to do a separation of scales as well, using a filtered mesoscale component as a mean function. And results are still pretty good, but
Right, I think that the important thing is what you use for the covariance function.
yeah, absolutely.
That you have some use when you're far from your data. It's not going to look like anything if you don't have the mean function there.
Right.
But where you have the data is where you really got your results, and that's where you really want to look.
Mm-hmm.
But the shape of the covariance function you start with, and you started with one that is isotropic in space and time. But when you were showing these, evolving patterns around the front,
Yeah.
you can see there are correlations in time with space that it's moving downstream in some sense. And so you could improve perhaps by putting a space-time correlation
Interesting.
and maybe a long front, cross-front difference in the length. And so you might be able to sharpen it a bit.
Last thing we do that I didn't mention is we also rotate the axis of the coordinate system to be in line with the front. So the x-axis is actually along the front while we do the interpolation. And then we rotate it back.
Yeah. So I would like to also, it's a very good question, because I was at MIT last week. We spent 2 days discussing exactly this question. Okay. So this essentially, it's what he's doing is machine learning. Okay. This is the kernel for the machine learning, and he's using half of the data to train parameter estimation. So it's like a form of machine learning. It's more like a leading edge. That's essentially what Raphael did. This is Raphael's work we are leveraging on for other applications. And also, what he's doing that's very kind of leading edge, and on top of that is again with Raphael's work, is that he's taking Lagrangian data, which is a bunch of trajectories, and he's projecting it to a field, velocity field, Eulerian, okay? And for a very hard problem where all the Lagrangian data collapse on a front, which is very hard, because if you can do this also from Lagrangian data only, but when the drifters collapse, those estimates go wild. Okay, so this thing works very well, and that's why we are using it. So that's again credit to the 3 folks in the front sitting next to each other, and we are further in this. So we are leveraging on each other's work, one PhD after another. So it's what's interesting.
Actually, we experimented with other functions, and Raphael can speak to that. And the remarkable thing is that the normal distribution works pretty well. It's pretty solid. Amazing. You can tweak some more, but this will get you 95% of the way. Actually, I'm sorry.
Sure.
Do you have the hyperparameters just out of curiosity?
No, I don't. Sorry. But
So this is not my wheelhouse or my field at all, but I have some questions. One, how deep do you think the oil layer tends to be? Because I'm curious, since you have the 5 centimeter versus 60 centimeter, kind of where is the oil actually? And two, I assume that water and oil have pretty different viscosities as well as other properties. So does this take into account the kind of dynamics of how oil moves and whether that would be different from what the drifter is experiencing or what just water is experiencing?
very, very good questions. Also kind of out of my field. Everything you said was pretty true. There's papers and studies looking into all of that. I don't have a clear-cut answer for you.
But I can answer. So we had this question in mind, of course. So we went to there's a lab in New Jersey. It's a 200-meter long tank, mostly for oil spill research, because you cannot put oil in sustained tank. You cannot put oil in the new pool, otherwise the teams will kill you. That's the first thing I thought. Well, let's put oil. So we went there and put our drifters, 5 centimeter drifter, 4 centimeter drifter. And also there was an oil spill that was leaking for 14 years near the Gulf. So this the Deepwater Horizon is the largest oil spill, but this one is the longest oil spill. 14 years they didn't realize. So we put on top of these things. So we found out that especially the shallow one is almost perfectly follows. The deeper one, or as you said, sometimes dispersion in the oil communities like thickens over the mix. So it depends on what kind of oil, but we are very confident that these things are good estimates. Like for hundreds of kilometers, they kind of, I picture them papers as just. So we worried a lot about it. Because that's the second question they asked. Oh, this is not oil, this is drifting. But then the biggest difference is oil over time, let's say 90% evaporates in 2 days. Okay, so it's not these drifters can, some of these drifters were found in Europe, Mediterranean Sea, we launched them in the Gulf Coast, we found Mediterranean Sea. So the oil is not going to go. It kind of dissipates.
And I also like the comparison between the drogued drifter and undrogued drifter because the drogued drifter is a lot more relevant to past observations. So we can kind of get a feel for how things might differ from past observations based on the drogued drifter as a reference point, and then compare that to what the top 5 centimeters is doing.
Yes, can you tell us a little bit more about the distribution of relative vorticity that you showed? Like it seems to be a hybrid distribution.
Seems to be what?
Well, it seems to have 2 modes, like 2 ranges of values. So is it a function of time, a function of space? What does that tell you about?
So the next one is for the entire animation here.
Yeah.
So all the points you saw through that animation is there. So I think what the bimodalness you're seeing is the front lining up, and then as that swirling eddy starts to form is when you get the left side of that distribution. And then once the eddy forms and it's completely dominated by positive relative vorticity is when you're seeing that second hump.
Maybe you could do a PDF as a function of time.
Yeah.
Time when the process is out.
Yeah, it's a great idea.
Yeah, they did a warm core eddy experiment years ago using remote sensing, Otis, Brown and company. And in the perimeter, you had essentially a ring with shear around the outer part of it. And it developed an instability which had a series of mini vortices, sort of like pearls on a necklace around the warm core ring. And I'm wondering whether the instability that causes the vortex that you're sampling is like one of these vortices, and whether there's some information in that warm core ring experiment that would allow you to understand the parameters for the formation of the vortices, or some measure of the scale length or something, because there is a difference in the water masses inside and outside, shear around the edge of the vortex and ring, and then you have these little mini rings all around it.
What were the authors on that?
Pardon?
What were the authors?
It would be Otis Brown was the lead. It was done by remote sensing.
Okay.
And I don't know. I think Don Olson was involved in the analysis of that, and I don't know whether they ever tried to analyze what the mechanism was for these mini vortices, or whether you could, for example, estimate what the scale length would be.
Yeah.
There's some sort of instability of that front around the ring, and it might be that there's some way that you could learn something from that data set that would inform what you're looking at. You have sort of a long linear frontal structure here, but that's just like a piece of this longer. I mean, these warm core rings were like 100 kilometers across or something like that.
Very, very cool. I like it. I'm in. James?
So since that part of the Gulf of Mexico has a lot of strong salinity gradients, did you notice any sensitivities in your part of the results from part 1, mainly the shear in that upper meter, the different spatial variabilities in salinity? Did you take a look at that at all?
Can you speak a little louder, James?
Yeah, so since there is such strong salinity gradients in that region that you're looking at, Did you see any sensitivities of the amount of shear that you were seeing in that upper meter to different distributions of salinity? Do you think that impacted your results at all?
The effects of the salinity distribution or the effects
Since
on
salinity
the
is-
shear?
Well, since salinity is going to affect the density of that upper meter,
Yeah.
do you notice any, I guess, changes in the percentage of the shear
Okay.
that you were seeing?
Now I understand. So since we were looking at such high winds, and we think we see that signature of increased deflection angles as the wind increases, which is a signature of vertical mixing. We didn't take into account really the stratification within that upper meter affecting the amount of vertical shear that we're seeing. But it is a very good question. Yeah, I'd point you to the paper, but I think that's the gist of the story there. But it does have an effect.
Not in this particular region, but closer to the coast, salinity is definitely driving. He didn't go into that because his experiment is really far from shore, but we had a lot of experiments where it was close to shore, and there salinity is like the number one factor. So it's a very good question.
I think comparing the Mediterranean is going to give an answer to that because some of the that is a lot higher. So you might find less in stress.
Now he's working on the Mediterranean versus, exact this question, Mediterranean versus Gulf, to be a data for Mediterranean, so we don't know anything yet. They don't look the same.
You said it's mostly the right spectrum, the right histogram is mostly dominated by divergence, by convergence, the red part. To my eye, at least, it looks like it's kind of balanced between the two.
Maybe within the meat of it, but there's definitely higher values in general. The tail definitely goes out a lot further, which you can be the judge of how much more that counts quantity over magnitude.
If you could break these down into where it is and what time it is,
Yeah.
then you could
Seems to be
see a
necessary.
whole lot more of
Yeah.
what's going on.
Or you can have also like a joint histogram of vorticity and divergence.
How interesting.
That would be really nice.
For the hyperparameters, are you like trading hyperparameters based on the data?
No, we're using all the data, all
So
the
you
different
train
data.
the hyperparameters and all that, and then use it to like extrapolate to make the velocity data. Okay. I was just
So the tuning is just done with the covariance function and all the observations that we have of velocity. So we have velocity x, y, t.
do those hyperparameters change in space? Is it
No, they don't change in space, but if you see, we're doing it over 2 sets of scales.
yeah.
I from 1 to 2. So right now the way it's set up is we have 2 time scales, 2 length scales in y and 2 length scales in x. And then we optimize those based on the observations alone. And then we basically build a little model using the optimization procedure that we fill in all the rest. That,
So to follow up on that, how do you verify that? Like, what do you use as a verification?
X-band velocity radars.
Okay, so you're
Or you have to,
okay.
yeah, you need some type of velocity validation to show what you're doing is actually
So if you
reality.
instead took a subset of your data,
Hand waving.
and tested it on that, on like your remaining, that's how you, like, that's how a typical machine learning project.
Yeah,
So
you
you're
could
not
definitely do
testing a
it.
different data set. Do you think you would have similar? Okay.
Similar, yes, but I think it would definitely be different. I mean, we have a lot of drifters, but not that many.
Yeah.
So I kind of, given the fact that we're trying to get down to the nitty-gritty physical processes, I like to throw as much data into it as I possibly can. And I didn't touch on this, but Raphael's method of velocity validation uses, so there's 2 training steps within the model. You can use all the data, and then you can save half the data the second time you train it, and then predict on those points. But I found that using that method and testing different either covariance functions or different pre-processing, like rotating the axis, or we've done some playing around with mesoscale filtering. I find that that way of validation isn't quite enough. They all validate kind of the same way because those points are already being put into the velocity reconstruction. So they produce very different velocity fields, but the error almost looks the same. So yeah, I think you actually would have to withhold some drifters fully to get a good velocity validation out of it. All right.